Alright, so in this video we're going to be going over kinetics. So kinetics deals with rate laws and reaction mechanisms. So how fast a reaction happens. So the rate of a reaction is the measure of change in concentration of reactants or products over time. So it can be measured as the decrease of a reactant per unit of time, or it can be measured as the increase of a product per unit of time. So usually we use a spectrophotometer in a lot of these kinetics experiments. So we can take a reaction, stick it into the spectrophotometer, and we should either have a reactant or a product that's colored, and we're measuring the absorbance over time. So basically we're measuring the concentration over time. And with that information we can come up with a rate law. So the factors that can affect rate can be surface area. So basically, if you crush something up, if you dissolve it, you're going to increase that surface area, and that increases your rate. You can add a catalyst, which will lower the activation energy. You can also increase temperature, which also increases the rate constant. And you can increase the concentration of the reactants, usually for most reactions. So the rate law is written like this. So it's written as rate is equal to K, which is the rate law constant, multiplied by some reactant taken to some power by the other reactant taken to some power. So the coefficients will only equal the exponents in this case if you're looking at the slow step. So if you guys remember in equilibrium, we could just simply look at the coefficients to get the exponent. But we can't do that unless we know the reaction mechanism, so the steps that the reaction goes through. So when we're looking at rate law, rate is determined by the slowest step in our reaction. That's why we can only look at the slow step for the rate law. So in order for a reaction to happen, molecules have to collide, they have to have enough energy, so they have to hit that activation energy, the minimum amount of energy, and they have to have the correct orientation. So when we look at this potential energy diagram, the reactants start off with so much energy. We have to go to the minimum amount of energy, the activation energy, and then they go through a transition state. So basically this is the point where they're making and forming bonds. They're not quite at the product yet, and then we go down to the products. So here I have an exothermic reaction because I'm releasing energy. Products have less energy. The hump is going to be your activation energy here. All right, so reactions that proceed in a single step with a single transition state are called elementary reactions. So each little step in a reaction is elementary. And basically, you're looking at how many molecules are involved in those steps. So if it only involves one molecule, it's unimolecular, or the first order. If it involves two molecules, it would be bimolecular or second order, and then so on and so forth. But usually we don't see more than 3 molecules being involved. So the rate order, if you have a rate law written out, you can determine what the rate order is by just looking at it. So you're basically just going to add not the coefficients or the subscripts, but the exponents. So A is to the first and B is to the second. So overall it would be to the third order. So this particular rate law would be to the third order. But if I was only looking for A, it'd be to the first. If I was only looking for B, it'd be to the second. So overall, the rate law, or the rate order, is 3, so it involves 3 molecules colliding with each other. But with respect to A, it's 1, and with respect to B, it's 2. Okay, so a 0 order reaction would look like this for the rate law. So it would be to the 0 power. Well, if you take anything to the 0 power, you get 1. So essentially, the rate is equal to the constant, so little k. Basically, if it's to the 0 order, you can increase the rate, that reactant, and nothing would change the rate. So normally, if you increase the reactant, you should see an increase in rate, but you're not going to see that with zero order reactants. So you're not going to change the rate here. Now, something very important to notice is this graph. Anytime that I graph the concentration and I plot it against time, I get a straight line, that's going to be a zero order reaction. So basically, if you're looking at graphs, you really need it to be a straight line because straight lines have constant slopes and K is equal to the slope. So K should be constant. It should be the same thing on every point of the graph. So if you graph concentration versus time, you already get a straight line, it's zero order. Now, first order, if you graph the natural log of A, or of some reactant versus time and get a straight line, that would be first order. So my rate law would look like this. So that means that the rate is proportional to the concentration. So if I double the rate, or if I double the concentration, I will double the rate. If I triple it, so if I triple A, I should triple my rate as well. And basically you can prove that mathematically too by saying, okay, I doubled A, I'm taking it to the first, so 2 to the first would be 2. My rate would increase by a factor of 2. Okay, so you might also see a radioactive decay problem. If it says anything about half-life, radioactive decay, you're going to probably use this equation right here. So half-life is equal to 0.693 divided by little k, and you can use that to get the half-life or little k. And the half-life is the amount of time it takes for half of that substance to decay over time. So after one half-life has gone by, 50% of it should have decayed. If another half-life were to go by, then another 50% would decay, and it would go down to 25%. So after every half-life, I have only half of my substance. All right, so the second order. Well, if I graph 1 over the concentration versus time, I should get a straight line. So it should be to the second power, and basically it's proportional to the square of the concentration. Meaning, if I were to double A, 2 to the second power would be 4. So my rate would go up by a factor of 4. If I were to triple it, well, 3 to the second power would be 9. My rate would go up by a factor of 9. All right, so I can determine the order with experimental data. So if I want to get the rate order of A and B and get the overall rate order, I can look at this experimental data. The first thing I will do is I will look for experiments where one thing stays the same. And then I will determine what's happening to the rate based on what's happening to the other thing that's changing. So let's look at experiments 1 and 2. Okay, so 1 and 2, B is the same. So something has to stay the same. So B is the same here, and A goes up by a factor of 2 from 2 to 1. So A doubles. Let's look at what happens to the rate. It also doubles. Okay, so what I'm going to do, I'm just going to say, okay, my rate went up by a factor of 2. And that's equal to, basically I'm plugging it into the rate law expression. I'm leaving K out because K stays the same, so it's not really going to impact this. Okay, so I'm trying to get the exponents here. So my rate went up by a factor of 2. Well, A went up by a factor of 2. My rate went up by a factor of 2. So 2 to what power equals 2? Well, that would be 1. If I take it to the 1 power, then it goes up by a factor of 2. So that means that x in this case is going to be 1. So A is to the first order. So now let's look at 1 and 3. So let's figure out what's happening with B. So for 1 and 3, A stays the same, and B doubles. If I look at the rate, well, my rate went up by a factor of 4. An increase by 4. All right, so let's do the same thing. My rate went up by a factor of 4. My concentration doubled. Oh. And we're trying to figure out what that power is. So 2 to what power would give me 4? Well, that should be 2. So basically, my rate law should be written like this. Okay, A is to the first, and B is to the second. So my overall rate order would be to the third. A would be to the first, and B would be to the second. Now, if I wanted to, I could also go further, and I could solve for K by basically picking any of these experiments and just plugging it into the equation. Okay, so now K is special. It has units that vary. So sometimes they might ask you, what are the units of K? So what you have to do is you have to decide what units you need to get the units in the rate. So rate will always be measured in molarity or some sort of concentration over time. So it's some amount over time unit. So in this case, rate is molarity per second. So we need to figure out what the units of K are in order to get that. All right, so I know the units of K, or rate, would be this. I don't know what K is, but molarity, or concentration, should be just molarity. So I have molarity, and I want molarity on the top, so that's good. I am missing seconds, though, on the bottom. But if I were to take molarity and multiply it by 1 over a second, I'm going to get my rate units. So it should just be 1 over some time unit. So basically, anytime that we have a first order, it's always 1 over some time unit. All right, so for second order, rate's still going to be this. I don't know what K is yet, but every time I have a concentration, it's molarity, and there's 2 of those. So if I look right here, well, I'm definitely missing a time unit. I need the S on the bottom. But I only have 1 M on the top here, so I need to get rid of one of these M's, and I'm going to put 1 down there to do that. So it should be 1 over a second and molarity, or it can be written like this. Anything to the negative first is basically under the fraction. Now, the reason I need the molarity on the bottom is so that I can cancel it out and then only have 1 molarity at the end. So for second order, it's always this. It's always 1 over the time unit and whatever the concentration is, or the amount, whatever. It could be grams too, not just concentration. So you can memorize the units for the first, second, and third. You probably will not see anything beyond that anyway, but I don't like memorizing things. Sometimes your memory fails you. All right, so let's go ahead and figure out the rate law for this and also solve for K. All right, so for this one, let's look at 1 and 3. So we're going to pick 2 experiments where something stays the same. So 1 and 3, A stays the same. And for B, it goes up by 3. Increases by 3. Well, okay, what happens to the rate? Oh, the rate stays exactly the same. So basically, I increased the concentration of B, didn't do a thing to my rate. So my rate didn't change, so it went up by a factor of 1 or nothing. And my concentration went up by 3. Well, anything taken to the 0 power would give me 1. So this would be a zero order. So basically, if they change the concentration and that doesn't do a thing to the rate, that means that your rate doesn't depend on that thing. So it has to be zero order. All right, so let's look at experiments 2 and 3 now. All right, so 2 and 3, B stays the same. All right, so A goes up by 3. If I'm going from 3 to 2. And then my rate goes up by 3 too. Okay, so my rate went up by a factor of 3. My concentration went up by a factor of 3. So 3 to some power equals 3. So y has to be 1. Okay, so when I write my rate law, it should look like this. Rate is equal to k times b to the 0, and then a to the 1. And this needs to be taken out because it doesn't impact the rate. So really it's just rate is equal to k to a to the first. All right, so if I want to get k, I can just pick any of these experiments. It does not matter which one. Let's pick the first one. So my rate is equal to this. I'm just going to plug it into this equation and solve for k. Is equal to k times the concentration of A, which is 0.1. And if I solve for k here, I'm going to get 0.003. And this is to the first order, so my unit should just be 1 over the time unit, which in this case is a minute. All right, so whenever you're doing this, remember one thing has to stay the same, the other thing has to be changing, and you're basically just trying to see what happened to the rate when you changed this thing. So you're trying to figure out the order of that particular item. All right, so the Arrhenius equation was taken out, but they do want you to know conceptually what that's about. And basically, the Arrhenius equation really just deals with these two relationships. Little k will increase if you increase the temperature, and also k will decrease if you increase your activation energy. So that's really all you need to know from that, or at least that's all I expect you to have to know. So k will increase if you increase the temperature, and that's also true for the equilibrium constant. Well, k will change with temperature, but little k will always increase if you increase the temperature. Little k will decrease with increasing activation energy. So if you increase the activation energy, little k should decrease. All right, so in our reactions, we have something called mechanisms. A mechanism is basically the steps that substance or those substances will undergo to get to your final products. So usually reactions happen in more than one step. The slowest step will determine the rate and the rate law. So if you have the mechanism, you can write a rate law if you know what the slow step is. So let's look at this reaction right here. Okay, this is our overall reaction. And then with step 1, this is my slow step, and then step 2 is my fast step. Well, my rate is only dependent on the slow step. So I can write out my rate law by simply looking at the reactants in that step. So my rate is dependent on NO, and I can look at this, the coefficients here. So it's to the first, and F2 to the first. So you can only write the rate law from a reaction if you know the mechanism and you know what the slow step is, because the slow step determines how fast that overall reaction goes. So we're just looking at the coefficients to get the exponents here, but we can't do it with the overall reaction because it doesn't show you what the slow step is. So if I were to write the rate law from this, it would be completely wrong. Okay, so an intermediate is something that is formed in one step of the reaction and then used up in another step. So basically, it is produced in one step, used up in the next. So let's look at our mechanism. Let's find an intermediate. So if I look behind this first step, I have Q, and it was produced here and then used up here. That is an intermediate. So Q is an intermediate. And then that's the only intermediate I have. So it's produced in one step, used up in the next. All right, so let's look at the slow step to get the rate law. Okay, so my rate is equal to little k times q to the first times b to the first. Problem is, this is an intermediate. We cannot write intermediates into the rate law because they're very hard to measure. So we have to substitute for whatever makes up that intermediate. So we're going to go back and we're going to find the step where Q is actually produced. Well, Q is dependent on A. So that means I can substitute the reactants that make up Q in this rate law. So my rate should actually be K times A to the first times B to the first. So I cannot use Q here. It's too hard to measure. So what I do is I go back and I look at the step where Q was made, and then I substitute the reactants that make up Q. Okay, catalyst will lower activation energy. Essentially what happens is that it will provide a different mechanism for the reaction to go through, which requires less energy. So it increases the rate by lowering that activation energy. So if you're given a diagram, that's what you should see happening to the activation energy with a catalyst. So the hump will be lower. So it will be a reactant in the first step, and then at the very end, when you have all your products, it should be completely unchanged, because that's what a catalyst is. It moves the reaction along, but it doesn't actually get used up or changed. Okay, so and let's find the catalyst in this. So we're going to look at the reactants that we start off with, and then we look at the products at the very end. And if it's completely unchanged, that is a catalyst. Well, Cl is the catalyst here because it's a reactant in the first step, product at the very end. So that's my catalyst. Let's see if I have an intermediate here. I have ClO and then ClO. So that's also an intermediate. So this is a catalyst because it starts as a reactant in the beginning and ends up as a product at the end. And an intermediate is produced in one step and then used up in the next. Okay, so if I were to actually combine these reactions, I would take out my catalyst and I would take out my intermediates and then just combine it. All right, so okay, so let's consider this mechanism. Identify the catalyst, identify the intermediate, and write the overall reaction. All right, so catalyst. Well, catalyst will be a reactant in the beginning and then a product at the end. So a catalyst would be an O2. All right, so the intermediate would be produced in one step and used in the next. So I have NO and CO2. My intermediate would be NO. All right, so I'm going to write the overall reaction. I'm going to get rid of my intermediates and my catalyst. So that'll go away, and that'll go away, and then I can just write it. So CO plus O3 produces CO2 and O2. All right, so in this particular question, we're going to label, or we're basically going to match the description to our potential energy diagrams. All right, so we're going to find an exothermic reaction with a two-step mechanism where the first step is slow. Okay, basically, remember, an exothermic reaction would have potential energy that of the reactants would be higher and the products would be lower. And an endothermic, I should see the opposite. Okay. Now, when it talks about the one step and the two step, well, every time I see a hump, that's an additional step. Because what will end up happening is, let's say I'm looking at this one right here. It goes into the first step. It makes a transition state. So bonds are being broken and made. And then it produces something right here. And then it goes through another step. And then that thing it produces is actually going to be an intermediate. And then right here it goes through another transition state. And then down to my product. So every time I see a hump, that's an additional step. All right, so let's look at A. So A says an exothermic reaction with a two-step mechanism, where the first step is slow. Okay, so let's find all the exothermic graphs. All right, so this is exothermic. Reactants are higher than products. This is exothermic, and this is exothermic. So it has two steps, so it can't be this one. This is just one. It has to have more than one hump. And the first step has to be slow. So if it's slow, that means that it takes longer to get to that minimum amount of energy. So basically, if this first step is slow, then the activation energy should be higher. So A should be this one. Because my hump here is higher, so it has a higher activation energy. So that first step is going to be slower than the second. All right, so let's do all the exothermics. Okay, so an exothermic reaction with a two-step mechanism where the second step is slow. Well, right here, I have an exothermic, I have two steps, and my second hump is higher, which means that it has a higher activation energy, which makes it slower. And then my other exothermic is with one step, so that should be E right here. All right, so endothermic with a two-step mechanism where the second step is slow. Okay, so an endothermic with two steps, so this one or this one, and the second step is slow, so the second step has to have a higher activation energy, so that has to be B. All right, so now let's look at this one. All right, so an endothermic reaction with a two-step where the first step is slow, so this one is higher than the second, so that one, and an endothermic with one step should be F.